the periodic table. Okay, the periodic table is actually the collection of all the elements discovered so far in a proper table form in order to make sure that it's easy for you to take information out of this table. Now, a few things about the table. First, the elements are arranged in the order of increasing atomic number. So they are arranged in such a way that 1, 2, 3, 4, 5, 6, so on and so forth, that goes in the same way. One atomic number is for hydrogen, the second one is for helium, the third one is for lithium, fourth one is beryllium, and the list goes on. Another thing we need to know are the two portions of the periodic table. The vertical columns are actually the groups. That is 1, 2. These are transition elements, 3, 4, 5, 6, 7, and 0. This can be 8, this can be 0. Why do we call it 0 and not 8 is something we'll clear ahead. Then we have lanthanoids, the upper yellow row, and the actinoids, the lower yellow row, right? And these horizontal rows are actually periods, and they're numbered in the way from 1 to 7 from top to bottom. So there are basically 7 rows or 7 periods in the periodic table. There are 8 different groups in the periodic table, apart from the centered set of elements, which we call transition elements. This is how we design it. Now, why do we design it this way? This requires further study. So let's go through that. The vertical columns in the periodic table are known as groups. The first 7 groups are numbered from 1 to 7, and the final group is numbered 0. The elements in the orange in figure 4.1 are called the transition elements, the ones that were present in the center, this one. The entire center are transition elements, all right? Transition elements are transition metals. At this level, they are usually not included in numbering of groups. Some of the groups have names. For example, group 1 is alkali metals, and group 7 is halogens, group 0 is noble gases. Let me tell you, all 3 of these groups are considered in much more detail in your course. So that's why they are naming them. Now, horizontal rows in the periodic table are actually called periods. This is important to remember that hydrogen and helium make up period 1. Let me clarify myself a little bit. This is period 1. We have hydrogen on the extreme left and helium on the extreme right-hand side. So period 1 has only 2 elements. If we talk about period 2, we have lithium, Li, Be, beryllium, and moving all the way to the right-hand side, boron, carbon, nitrogen, oxygen, fluorine, and neon. So we have a total of 8 elements in period 2. And just like period 2, we have 8 elements in period 3. And then moving on, period 4 and 5 has most number of elements. If we talk about period 6, take a look. It starts from CS, then BA, then this one dot, which means lanthanoids. This entire row of 14 elements is a part over here. But we don't put them here in the periodic table because then they will interrupt the position of these elements coming after the lanthanoids. Just like period number 6, period number 7 is also a set of elements, 14 to 15 elements that are actually known as actinoids. And instead of writing them as a part of the original table, we actually take them out and write them separately, so as not to disturb the position of these elements. All right? That's how we design it. And there are actually very important logics in this design. So the horizontal rows are called periods. It is to remember that hydrogen and helium are the only 2 elements in period 1. Lanthanoids and actinoids are usually dropped out of their proper places and written separately at the bottom of the periodic table. There is a good reason for this, because if you put them where they should be, the periodic table would be much bigger. If we put them these 2 lines over here, they would disturb the entire periodic table, and it would be much difficult to read. So to make it easy, we have taken them out of the table and combined the rest. Now the periodic table, number of protons, electrons, and neutrons, it's very easy to work with. The rules that we just studied in the previous chapter, the 3 rules, that the atomic number is actually number of protons and number of electrons are equal. And to find out number of neutrons, we take the bigger number and we take the smaller number. the smaller number, atomic number, is subtracted from the bigger number, which is mass number. All right.
Yeah.
Okay. Now, the arrangement of electrons. Electrons move around the nucleus in a series of levels called energy levels or shells. Just a second before we go with this diagram, actually. Previously, scientists used to draw it like this. Let's consider the innermost part of the atom as nucleus. Let's consider this one as the nucleus. And the electrons will then be present in the first shell or the first orbit or the second orbit or the third orbit. The scientists used to draw it like they used to draw the solar system. Actually, they were very inspired with the solar system, and they used to think that atoms exist like solar systems do. And yeah, they actually somewhat like do. So these actually shells, which I'm calling shells or orbits, are considered as energy levels or shells. The energy level is a much better term. Each energy level can hold a certain number of electrons. Lower energy levels are always filled before the higher ones, which means the ones that are closest to nucleus. This one is the closest to nucleus. This one would be filled first. When this is completely filled, when we'll start filling the second one. When this one is completely filled, we'll start filling the third one. So we go from nearer to the nucleus or closest to the nucleus, all the way to the shell, which is farther to the nucleus. Let's take a look. If the nucleus is present at the bottom, they are not considering circular diagrams anymore. They consider a writing like this. If nucleus is the center, the first level, this one, can only have room for 2 electrons. The second level, this one, can only have room for 8 electrons. And the third level, for the first 20 elements, the third level can hold a maximum of 8 electrons. For the first 20 elements. After moving from 20 elements, they may contain more. So this is the maximum number of electrons for first shell or first level. This is the maximum number for the second one. For the third one, we don't tell you the maximum number, but we write it like this. For the first 20 elements, maximum of 8. But after the first 20 elements, they may contain more. May. All right. But here we draw a boundary line and we're not supposed to go any farther than that. Okay?
Yeah.
Good.
That's 2, 8, 8, and so on.
For the first 20 elements, yeah. And then we start filling the fourth level. After filling 8 electrons, in the third one, we start filling the fourth one. And we usually use the word or the term that having 8 electrons in its outermost shell, which can be second shell or subsequent after that, all right, it is stable. It means having 8 electrons in second shell, it would be stable. Having 8 electrons in third shell, it will be stable. And as soon as it is stable, you can start filling the next shell.
So how many electrons can the fourth shell hold?
Which one? Third shell or fourth shell?
The fourth.
Actually,
After
if we
the
talk
third.
about the third shell, it can hold a maximum of 18. However, at your level, we say after 8 electrons, we'll start filling the next one. If we talk about the fourth level over here, it also becomes stable at 8 electrons. It also can become stable at 8 electrons, but that's not the maximum it can hold. The actual maximum it can hold are 32 electrons. But this 32 and this 18 is not a part of your course. So you're supposed to fill them with 8 electrons and move on for the fourth one, fill them with 8 electrons as well, move on to the fifth one, so on and so forth. The good part is that we only discuss the first 20 elements in your course in case of this leveling or this diagram. So it's very easy to work with because we are only require the first 20 elements. Those are the easiest one to fill.
So in my course, we'll only use 3 shells for every example.
No, you're going to use the fourth shell, but you're not going to completely fill them. Instead, you're going to fill them to a maximum of 8 electrons. That's what we're supposed to do. All right, let's clear it up. Just a second. Okay, so the arrangement of electrons in an atom is called electronic configuration. They're going to take the example of chlorine and work their way so that you can understand it. Now, the atomic number of chlorine is 17, which means it has 17 electrons in total. Now, if we talk about the first shell can only hold a maximum of 2 electrons. The second shell can hold a maximum of 8 electrons. And when we move on to the third shell, as we have already put 2 electrons in the first one and 8 electrons in the second one, we can only put a maximum of 7 electrons in the third shell. That's where it stops because it has a total of 17 electrons. We can't put any more than that. How are we supposed to write this? 2, 8, and 7 is something given over here. We're supposed to write it like this. Electronic configuration is written with numbers and commas. Now, the first number mean represents the number of electrons in the first shell, comma. The second number represents the number of electrons in the second shell, comma. The third one represents the third one, and so on and so forth. So 2 electrons in the first shell, 8 electrons in the second shell, 7 electrons in the third shell, and that's about it. That's for the electronic configuration of chlorine. Clear?
Yeah.
Okay. So once again, the electronic configuration is asked up till the first 20 elements. To clarify an element out of a fourth table, let's consider potassium with number. My bad. Just a second. Potassium with a number of 19. So there can be 2 electrons in the first shell, no more than that, 8 electrons in the second shell, no more than that. Then we put another 8 in the third one. Third shell becomes stable with these 8 electrons, so we start filling the fourth shell, and it will only have 1 electron. And if we add these up, 2 plus 8 plus 8 plus 1, the total is equal to 19, the atomic number. So the electronic configuration and atomic number both reinform one another, conforming each other in such a way that the addition of the numbers for electronic configuration adds up to the atomic number of the element you are working the electronic configuration for. This is more like a check of your own work. You can check out whether you are working it correctly or not. Clear now?
Yeah.
Okay. Let's move on. Now drawing the diagrams. When we draw the diagram, we draw circles to represent the energy levels. And we use dots or crosses in those circles to represent electrons. Hydrogen has only 1 electron, so it's the easiest one to draw. Helium has 2, and both in the first shell, the lowest energy level. Moving on, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, you would see all of their first shells have 2 electrons. And we started filling the second shell from 1 electron in lithium all the way to 8 electrons in neon. Take a look, 1 electron.
Does the placement of the first 2 electrons in the first shell have to always be like that?
What are you talking about? The pairing of electrons, placement,
The placement of the electrons in the first shell.
Okay, let's talk about the placement. In the first shell, we usually put both electrons in the form of a pair. When we are putting the electrons up in the second shell, they are usually put in such a way that we use the plus sign like this. So 1 electron over here, 1 over here, 1 over here, 1 over here. And then we start converting them into pairs. This one has been converted into pairs. These 2 has been converted into pairs. And then these 3 have been converted into pairs. And finally, the plus sign has completely converted into pairs for the second shell. And yeah, the placement has to be like this. It's a pattern that everybody follows, be it a teacher, a student, a researcher, a scientist, everyone follows the same pattern. I hope I have answered your question, but if were talking about something other than this,
Yeah,
about
you
placement,
answered it.
okay, good. Then let's clear it up and move on, because this is simply an addition of one electron at every step, moving all the way from lithium to neon and completing the 8 electrons in the second shell. Because every single one of the atoms shown over here have already the first shell full. So they are fulfilling the second shell from 1 electron in lithium, 2 in beryllium, boron, carbon, and all the way to 8 electrons in neon in the second shell. Okay, so you can draw electrons singly or in pairs, but it's better to draw it in pairs. Let's move on. Now this one is the potassium I was talking about. Potassium and calcium are 19th and 20th element of the periodic table. So 19 means it will have 2 electrons in the first shell, a total of 8 electrons in the second shell, another 8 in the third shell, and there's just 1 electron in the fourth shell for potassium, and there are 2 electrons in the fourth shell for calcium. The rest of the configuration stays the same. That's why I was saying that the electronic configuration of the first 20 elements is something you're supposed to do for these exams. This is the electronic configuration for the first 20 elements. They're emphasizing on the same thing over here. And I think it's pretty easy to read and judge that, let's say, if we are talking about sulfur, sulfur would have 2 electrons in the first shell, 8 electrons in the second shell, 6 in the third shell, which means it has the atomic number of 16. Because add these 3 numbers up, you'll get the atomic number. All right.
Yeah, okay.
Now, this page also states 2 important facts at the second half of this page. Elements in the same group in the periodic table have the same number of electrons in their outer shell. Take a look. 1 electron in outer shell, 1 electron in outermost shell, 1 electron in outermost shell. Why? Because they're in group 1. 2 electron in outermost shell, the last number, I'm talking about this 2. 2 electron in outermost shell, 2 in outermost shell, 2 in outermost shell. Why? Because they're in group 2. Group 3 has 3 electrons in its outermost shell. Group 4 has 4 electrons in its outermost shell. Group 5 has 5, 6 has 6, 7 has 7. That's why we number these groups as these numbers 1 to 7, because this is the number of electrons they have present in their outermost shells. Now this is the same as group numbers from 1 to 7. However, you would see that we have been using a different number for group 8, and that is 0. Although this has 8 electrons in its outermost shell. Take a look. This one has 8 electrons in its outermost shell. This one has 8 electrons, but this one is an exception to this group. So instead of writing the name group 8, we don't use it because there stands an exception which does not have 8 electrons in its outermost shell. We call it group 0. All right. That's the reason why we call it group 0. There is another reason behind it, which we are going to discuss a little later in the same book. But the first and foremost reason is that this is the only group in which lies an exception of helium, who does not have 8 electrons in their outermost shell, hence a different name. Clear?
Yeah, okay.
Okay.
And then the periods correspond to how many outer shells they have. Yeah.
How many shells they have?
Yeah.
Outer shell means the last shell, the one having the
I
most
mean,
energy.
how many shells in total?
Right, right. For example, calcium has the electronic configuration of 2882. Then this is the first shell, second, third, fourth. This means it has 4 shells, or it's in period 4. And the last number is 2, which represents it's present in group 2. That's how we work it out. All right?
Yeah, okay.
Okay. Let's keep moving on. Elements in the same group in the periodic table have the same properties. In order to prove his point, he has given examples. Let's go through the first example. All the elements in group 1 react vigorously with water, form the same compounds with the same formulae, and that's why we say that the periodic table, the word periodic means that the patterns can be seen in similar groups or periods. And the first of those patterns is that groups contains elements with similar chemical properties. Take a look at group 7. All the elements would react with hydrogen to form similar formulae, acids, HF, HCl, HBr, so on and so forth. So all of them react in the same way. All the elements in group 2 form chlorides with the similar formulae such as MgCl2, CaCl2, SrCl2, so on and so forth. So all the elements present in a group work or react in almost the same way. All right. And the reason I was explaining to you about group 0 of helium being an exception is written over here. Okay. So let's move on. Let's raise this one up. Noble gases. This is the last group, group 0. We call them noble gases. The word noble means a good person, but here, in this case, noble means that the gases are completely unreactive.
They are unreactive because their outer shell is full, right? Therefore,
Right.
they don't need to lose or gain any electrons.
Correct. That's correct. So the fact that 2 at the top of the group, helium and neon, don't react with anything, the elements in group 0 have 8 electrons in their outermost shell, apart from helium, which has 2, and their lack of reactivity is actually associated with having complete shell. And that's why the name group 0. It does not need to lose, gain, or share electrons in order to go with a chemical reaction and form compounds. That's why group 0, because of 0 reactivity. It doesn't mean they won't form any compounds at all. Extension work tells us that in some cases, krypton, xenon, and radon have compounds with other elements as well. But they have so little compounds that we are aware of that we still call them unreactive.
So in no case, noble gases react with any other elements.
There are cases in which noble gas react with other compounds. For example, we have compounds of krypton with fluorine or xenon with oxygen and fluorine. But those compounds are so less that we still consider them unreactive. All right.
Okay, and does displacement also play into this fact? Like,
Which specific displacement are you trying to talk about here? There are many kinds.
like if there was a noble gas reacting with another noble gas, is that possible?
That might be possible, but I haven't seen a reaction like that so far in my life.
Okay.
Not at least at this level or A levels. Yeah, this happens with metals and non-metals, and we tend to term it in such a way that we say more reactive metals can displace the less reactive ones, or more reactive non-metals can displace the less reactive ones. However, in case of noble gases, they are so unreactive that they usually do not tend to replace one another. So if there might be a reaction under some specific conditions, I probably am not aware of that, but I haven't so far seen a displacement reactions in noble gases, because only a few of them react with fluorine and oxygen, and that only with fluorine and oxygen, no other metal or non-metal in the periodic table. Okay, so let's bifurcate the periodic table in another way. We can bifurcate the entire periodic table into metals and non-metals. Let's discuss what are the properties because of which we call a metal or a non-metal a non-metal. Now, what they did is that they colored the entire periodic table into metal and non-metal, metals in blue, non-metal in yellow. And you could see that more than 75% of the periodic table is just metals, right? So what are the differences in between metals and non-metals? To start with, electrical conductivity. Metals conduct electricity, non-metals do not, right? But there might be an example of non-metals which can be conducting electricity as an exception. That is going to be graphite, and he specifically stated a chapter which is going to explain that. Non-metals do not conduct electricity. They don't have any electrons free to move. They don't have any ions free to move. Graphite is the only form of carbon or silicon that are capable of letting the electrons move. And let me tell you, silicon isn't considered a complete metal or a non-metal. Silicon is actually considered as half metal or a metallite, means a mixture of both, an element that has a few properties of metals and few of non-metals. Okay, so metals generally form basic oxides. Whenever they react with oxygen, they form a basic oxide. A basic oxide is an oxide which can react with acid to form salts. This is the example given over here. Take a look. Copper is a metal. Its oxide can react with an acid, can form salt and water. Non-metals, on the other hand, form acidic oxides. Let me quote an example over here. Let's clear this up. Take a look. Carbon or sulfur are non-metals with their oxide, sulfur dioxide or carbon dioxide. They're known as acidic oxides because whenever they react with an alkali, they form salt and water. This was a basic oxide because when it reacted with an acid, it formed salt and water. This is an acidic oxide because when it reacts with the base or an alkali, it forms salt and water. All right. That's the second way to differentiate that. Let's keep on moving and let's discuss different ways they can be different. Metals tend to be solid, high melting and boiling points, high densities. The only liquid metal on the planet is mercury. Non-metals tend to have low melting and boiling points. However, there are some exceptions such as carbon or silicon. In case of carbon, diamond has high melting or boiling points, or graphite does. In case of silicon, silica does. Metals are shiny. They have a metallic luster. They are polished or freshly cut. Non-metals tend to be brittle. Whenever we try to shape them, they break. Brittle means that it has a rough surface, and when you're trying to force it to shape it or to reshape it, it breaks instead of getting shaped when they are solid. Now the metals are malleable and we can hammer them into shape, so much so that you might have seen matchboxes at your home. Matchbox is this much a piece of cardboard. Matchbox is of really small size. If the similar size of gold is taken and we hammer it up manually, we can turn this piece of gold into a sheet as big as the biggest football stadium on Earth. And that by just manual hammering and not using any kind of machinery. That's how much metals are malleable. And it's not just about converting them into sheets. Actually, we can hammer them into many different shapes. And you can see metals are used for making cars, and many different shapes are used in different parts of the car. On the other hand, non-metals, as we have discussed, are brittle. They don't have any shine. Now, metals are also ductile. We can pull them or stretch them or draw them into wire. I think stretching or pulling gives you a very good idea how we convert them into a wire. On the other hand, once again, these are non-metals and non-conductors. Non-metals are non-malleable, non-ductile, and non-conductors. Metals, on the other hand, are good conductors of both heat and electricity. Non-metals are poor conductors of electricity except for graphite, and poor conductors of heat except for diamond. Make sure you remember the exceptions because these exceptions are usually considered for tricky questions or tricky MCQs, multiple choice questions, all right?
Okay.
Metals usually will tend to form ionic compounds. However, non-metals, if we keep on moving, you would see that non-metals would tend to form covalent compounds. However, they also can participate in forming ionic compounds. Now, metals will tend to form positive ions by losing electrons in their compounds, and non-metals will tend to form negative ions by gaining electrons in their ionic compounds. So we have many differences among metals and non-metals. And when we bifurcate the entire periodic table, all of them which are metals show the properties of metals, and the ones that are known as non-metals, which is roughly 25% of the periodic table, show the properties of non-metals. These. Fair enough. This finishes our chapter.